Jose spoke yesterday. AO takes out, talk about the atmosphere moving. And so the problem with these effects is that they can all too easily mimic what's going on the sun itself, the motions and the time scales and that we see on the sun. The dispersion was nice. We don't expect images to wander precisely like that. But today we're looking at some effects. And so we see these images, movies we get from space sometimes, right? We get these nice scenes of granulation in this case, taken from Hinode and the G-band. We can stabilize those, and they come out these nice, beautiful, smooth movies. And this looks really great. You can see all these little bright points bouncing around in the intergranular lanes, convective motions. That's all great. There we go. We can also get nice movies from the ground, and sometimes, we've seen these nice movies. This was taken with a dot telescope over here in the calcium K line near the limb. And so you see all these nice motions, wonderfully stable, beautiful. Here we see H alpha observed on the disk with IBIS, and you see these up and down motions of the dynamic fibrils, and you're able to track those and see them very clearly and see how the sun's moving. And, so these are the, nice movies we see also from the ground. And so we're like, okay, great, that looks easy. And here's a nice movie, again, going back to the granulation now, taken from the ground. Looks kind of like the one we got from space. See a little bit of flickering and changes there occasionally, but overall it's pretty stable, and so doesn't look too bad. But what's important to realize is that the data that made this movie started out like this. This is the movie after the instrumental calibration, right? This is the level 1 data. You have atmospheric motion, you have rapid changes in the seeing. The image moves a little bit because of AO. You have some bad frames in there where the seeing just went completely bad. And so the trick is to get from this to the other nice movie to this, right? This is what we want, is to get the nice movie and take out all this kind of funny business. And so, that looks terrible. Why exactly do we want, these are nice movies. Why? What's the science? Why do we need these stable images beyond just being able to be impressed and amazed? We want to be able to look at the evolution of features, right, in the solar atmosphere. We want to be able to find a feature, follow it in time, see how it's evolving and moving through the atmosphere, like those bright points. We want to understand that motion. Sam studies that, how these bright points get bounced around, and that tells us things about the nature of the photosphere. We want to be able to measure the horizontal flows in the photosphere or in the chromosphere, and in order to do that, we need to make sure we're not confusing ourselves with image motion from the Earth's atmosphere. And finally, we also want to be able to perhaps co-add data. We want to take a bunch of data and combine them together to improve our signal to noise. As we saw yesterday, sometimes a few seconds isn't enough. We want to be able to add 10 seconds or 100 seconds. And in order to make that sensible and actually reduce the noise, we need to make sure we're adding the same spot on the solar surface as we do that summing. And we're actually building up the signal. So I'll show you another example of some of the steps going from one to the other. So this was some data that Jue and I took, and Momo at Big Bear in H alpha. So this is with the 1.6 meter telescope, and it's a sunspot, and you see all kinds of neat things going on there with the chromospheric structures and brightenings. And so this is one of these nice stable ground-based movies. So this is the data we got from Big Bear. So they have image rotation. They don't have a derotator, even a CUDA platform. But as we saw yesterday, there may be observations where the image is going to be rotating because we want that slit to be fixed along that parallactic angle. And so that means our imagers will be seeing a rotating image during the day. And so we'll have to take out that image rotation. And we can do that, and now the image is derotated, and it looks, you can see the sunspot isn't moving here, but there's still some residual image motion and jitter there. Yep.
Did you derotate it with an analytical formula, or did you
It was,
follow the PE?
no, it was derotated just with an analytical formula, as if for DKIST we'll know what the angle is at any given time, but you need to take that out. Theirs, it's a constant rotation at Big Bear. Now we can just do a rigid alignment where we just take the whole image and shift it to get that alignment. And now you see the image is is more stable. Now this feature here, if you follow it, they're sort of staying in the same place over the duration of the time series. And we can go through one more step and now run a de-stretching algorithm on it that I'll explain later. And now you see finally we have a nice stable movie. There's no more jitter or image motion in there. And so by going through a series of steps, we're able to get that sort of end product. And now we could, pick out the points here in this little light bridge and study the convective flow right along there and know we're not, seeing other things drifting into our field of view. We're not getting the right time series out. So all these things, there's a series of atmospheric effects that are causing a lot of these problems. The rotation is from the telescope, but the rest is either atmospheric or perhaps from the telescope or AO system. And so we'll go through a few of these and look at them. The simplest one is that was mentioned yesterday, the transmission changes during the course of the day. This doesn't cause any image motion, but you just do have a light level. The total throughput of the atmosphere, depending on the wavelength, will vary by as much as a factor of 2 during the day. And so your signal to noise may change, so you may have a different sensitivity in the morning compared to if you're observing later. Scattered light may go up. And you may get hit at times with clouds coming through. This actually happens not infrequently on Haleakala. The fog builds up in the crater. If the winds are right, they blow it up out of the crater. And low-level clouds tend to drift through at some height. Maybe DKIST will be high enough it won't happen as often, but that happened at Mies a lot, at the previous observatory up there. And so in order to sort of take out this intensity, we don't have a real-time calibration. We basically, from solar telescopes, we just normalize to the continuum. We reference that to a model spectral fluxes at a specific wavelength, and or we just normalize to the mean of the sequence and normalize the intensities that way. So that's a fairly simple problem to deal with, just an intensity fluctuation. The bigger problem, and Jose showed this yesterday, and John as well, everyone's shown it. So this is the seeing during the course of the day, and you see how it gets better and then fluctuates around a lot. So there's a lot of fluctuations in the seeing in the course of a day. And how do we measure that, right? That's what we want to know, how those, as the seeing gets better or worse, we want to be able to find our images that have better or worse seeing. And one traditional way is to measure the image contrast, especially if we have a nice quiet sun where we have granulation. We sort of know what the contrast typically is at a given wavelength. We can measure that contrast, just take the image after flat fielding, take the RMS of that image and divide it by the mean. And so what that tells us is that the fluctuations in our image in this time series here was about between 2 and 3%. And that just tells you how many sharp features you have in your image, so it's a good measure of whether you have those granules are bright and dark or whether they're all just washed out into a soup. And so here you see a few times where that RMS drops significantly down like this, and then it comes back up quickly. For a comparison, this is that scintillation measurement plotted, measured at the same time. This measurement here, this kind of measurement. And it's mildly correlated at some times. But you really want to be able to measure from your image, your actual image, what the contrast is. Hopefully AO will also tell us what the R0 was, that measurement of that aperture of the seeing based on the coherent patch of the atmosphere. So that'll also tell us perhaps what the quality is, though again, there's some variation with wavelength. And that tells that just at the lock point of the AO, we may have a whole field of view, and we want to know how the performance is, how the image is over the large field. There are other techniques out there to do this. There's a technique that's been developed by Deng and Denker, looking at what's called the median filter gradient similarity, where you take two images, or you take an image and you smooth it, and then apply a convolution kernel, a shifting, and you look at the edges, compare the edges in the median and the original, the raw image. The GR is the raw and the GP is the filtered. And you can see it's sort of, they argue it's a little better than the RMS, a little more robust, and that may be true. What is interesting is just how much this fluctuates in time, right? This is all of 12 seconds here, and you see the fluctuations can be very rapid. So you may have patches of good seeing, and then you may have 5 seconds or 1 second where the seeing's bad, and then it comes back. This also, depends on AO and so on. So there's a lot of rapid variation. It's not just, the seeing goes bad and then all the images are bad. And a lot of times you want to be able to compensate for that, jump over those bad, you don't want to stop or interrupt a whole series you have just because there's one bad image. So we want to be able to find where those bad images are and take those out using some automated, some metrics like these. A lot of times it just, you need just a visual measurement, right? Depending on the number of images you have, you can just look and see where the bad images are. You can use these two together, perhaps. This is a plot of this mean, the mean filter gradient similarity over here, over that time period I showed before, and then comparing that to the contrast. You see they're somewhat correlated, but maybe the contrast is higher here, even though the MFGS gives a lower value. So there's not a unique measurement. The problem is we don't have a reference, right? We don't know what our actual image should be at any given time. So we have what's called a reference-free. We need reference-free metrics to evaluate these, and those are hard. Bad seeing can sometimes provide high contrast. If you have multiple images shifted, you may get a nice high contrast image, but it's only because you've shifted, the image has jumped around during the exposure. So that's why sometimes it's necessary to fall back on just looking through the images and finding them by the bad images by eye. So that brings us to our first exercise. So the first exercise is to find some bad images in a sequence of data. So this is a time series of data, 100 images. That's on the Google Drive and it's on the server. There's a FITS file. And so you can try scanning through those images, looking visually. You can try just calculating that RMS over the mean, looking at the contrast to see where the images are bad, or where these blurry images are. And there's a IDL program. Jonathan has made an IDL program, and Momo that does the MFGS calculation. It's an IDL still, but there's a Python version, but it's not. I don't have it in the Google Drive yet. So right. I mean, on the server, the file's there in this this directory. There's the FITS file. It's 400 megabytes. You can download it from the Google Drive if you want to do it on your own computer. And any FITS reader, you should be able to open it up and look at just at the series of images. Or you can log in and look at the images there. And the idea is that in that Google Drive, there's a document called Bad Frames List. Everyone can put their decision on which frames are bad in there, and we see if everyone gets the same answer. Some people are more lenient than others about which frames are bad and which aren't. So we'll take some time now. Everyone can take a look at this time series. It's only 100, so you could even step through and look at them all, but DKISS, there may be more than 100. Well, I mean, this is 100 out of over, I think, over 10 minutes, and it was taken out of about 2,000 images. So, yeah, it's this is already down selected to make it manageable. Yeah, it's called XMove. There's yeah, it allows you to step through or play a series of images as a movie here. So we'll go through. Up, yeah, it's pretty bad. I don't know, maybe. Then, it's good for a while. Oh, then it goes. Yeah, that's pretty bad. That's bad. Oh, that's terrible. So yeah, get rid of that. That's bad. That's kind of mucky. So one thing, so we'll go through here, get some more. So back, where'd it go? That's okay. So some here. So that one's bad. Now one thing, you're trying to build up a time series, right? And you don't. So if one image is bad and the two around it are fine, then you're at the lower bar in some sense to dropping it, because you're like, I've got information on each side. I'm going to be, sort of interpolating in between to compensate for that missed image in my time series. One image is fine. When there are blocks here where it's 4 or 5 images, then the ones on the end where it might be on the borderline, you might say, well, that one's, maybe it's okay to keep that one because it has, not that one. Like this one, maybe that, has some. So this is a problem that the whole thing, it's complicated. You're trying to maintain that time series, but throw out the images that are not going to be contributing anything useful. And there's no unique way to set that threshold. As you saw, you can calculate the RMS, but which ones are, there's not a for any given image sequence, there's not one threshold you can apply across all images. The granulation, the contrast changes with wavelength. If you're pointing off towards the limb, the contrast will be different, so there that natural contrast will be lower. And so there's a lot of variability in those metrics, and they sort of need to be tuned, and trying to find ways to have metrics. I mean, that was one goal of that MGFS, was to have a metric that was less dependent on the underlying structures and more dependent on the variability of the contrast as a function of time. So yeah, we had, what was this? Did everyone get 75 in their list at least? Yeah. Mm-hmm. So, and as we'll see now, we're going to be looking these time series not just scientifically. We want to be able to see waves flowing and track features, but we're also going to need that time series in order to disentangle some of these the solar motions from the atmospheric effects. So that time series is going to be crucial in some of the coming steps as well. So having that nice stable time series where we can sort of track features from good image to good image is going to be an important thing. So this is probably the most annoying step for ground-based data for me, is trying to sort out what's good, what's bad, and deal with that large variability. Hopefully there's a variety of tools able to make that easier with DKISS, but the underlying problem is, in some sense, will remain. So oh, came up over here, sorry. Look at there we are. So we did that first data sorting exercise. Most importantly, we've all downloaded, I think, the data. We're going to be using that same big block of data in the other two exercises, so we won't have to have any more big downloads. So that's good. We have this time series, and I think now we know which are the good images. And so we'll get rid of those jumps. Sorry. So those images, there's still some jitter in there. You can see the image still moves around a little bit. It's not always at a fixed position. And so we want to be able to line these images up now. So we have a time series where all the images are pointing at the same point on the sun, and co-aligned with a rigid alignment. And so we need to look at these images, but of course we can't just take the first image and line everything up to the first image, because this is a time series covering almost an hour, or this one's even 15 minutes, and the solar granules are evolving. So if you start trying to keep lining up on a single fixed reference, you're going to end up sort of getting off. Your correlation's going to not be robust anymore. So we need to be able to correlate one image with a successive image, and then build up our alignment based on that. So, and then cumulate those offsets. So each image we reference to the previous one, and then we can cumulate those shifts and get the total drift of the image with time. So what happens if we don't do that? So this is now what we call an XT slice. So we've taken a slice across. We have our data cube, X, Y, Z. We've taken a slice in the X direction here, going across the data cube. And then we have the Z axis going up in the other direction. And so in one image, if we take a slice across, we see the granular intensities, intergranular lanes, and those have some constancy in time, and we see those as these sort of vertical features, that granule that's persisting from image to image. But then we get these spots here where we had the bad seeing, right? The frame 16, 17, and up here in 49, and so on. So we see those spots where the seeing's bad, and we see that there's also times where the granular features seem to be discontinuous. Yeah. Yep. The other one, right? The wrong place. So, is that better? Yeah. So obviously the granules aren't just jumping around from one image 10 seconds later. They've jumped to someplace else. So what this is, the image motion. There's residual image motion. This is from the atmosphere. This is from AO. AO is tracking on the sun at some point, at some location on the sun, but that feature that it's following may be moving on the sun. It may require a new reference to track on, and so it'll change in time, and you'll get some motion of the image. So we want to take that out so we can follow these granules in time. And so we can just take each image and do the cross correlation, like Jose showed yesterday, matching up your strawberries, right? We have one strawberry here, and now it's over here, and we do the cross correlation, and we see where the peak of that is, and that tells us what the shift of the image is. And we apply that to the whole image at once, or most of the image at once, and we can calculate what the rigid shift of the image is. And we just do that one image to the successive image, and we get this sort of this fluctuating pattern of shifts. Sometimes the image jumps here. You see some of these large deviations are where there's a large jump from one image to the next, and then it's stable in one position, and then it jumps again. And then we do the cumulative sum of these shifts over the sequence. Going the wrong way. And now I see that there are some, these shifts show this slow trend where the image is drifting. The blue is in the x direction, the red is in the y direction, so there's some drift, some trends in the image drifting over time, and then there's some smaller patterns of jumps on top of that, smaller scale. So something happened here, the image jumped for a bit. So this tells us what the shifts are, then we can apply those and apply the same shift just in the opposite direction and take that out and line up our images. So that's our next exercise, is finding those shifts and trying to line up the images. So this is, there's some process here. You can do an IDL, where it basically uses this program called XYOff, which just does a cross correlation between these two images over a central box of 800 by 800 pixels in this case, and then does the cumulative sum of those shifts, right? So it's doing each image to the previous, the NN-1 image, and then it sums those up, and then you can just apply a shift and line the image sequence back up. And so the idea is if we can get a nice co-aligned sequence of those images and see if see what it looks like after once they're co-aligned, how that looks. So this is an IDL again.
For those that use Python, can you?
I mean, this can all be.
The logic?
So the logic is you have your sequence of the images that you have, the same 100 images. You're just measuring a cross correlation. And I forget what it is in Python, but you're just measuring the cross correlation between the two images and finding the peak of that correlation. And that tells you what the shift is saved into this array of offsets, one x and y, so it has two coordinates, an x and y shift for each image. And then it just sums in E separately in the x and y direction, sums up the total amount of the shift at each time step, the total shifts up to that point, and puts them in this summed array, and then applies a shift to the original array of those images, putting them in a separate array for convenience, and then that should be a nice co-aligned array of the white light images. So the bad frames will still be in there. So it may be useful to take out those bad frames. You could take those out of the array. It should work even with them in the array, but you'll have a nicer time series if you drop them from the array. Then you don't have the blurred images in there. So yeah, this is a little bit more. A few more steps here, but we can answer questions. Hopefully it works. So here's the resulting movie that's now been aligned. This one still has those bad frames in it, so you see some jumps there. Overall, it looks a little more stable, and the real proof in said pudding. that was the alignment there. Scroll forward here. Yeah, so there's the movie. You see it's fairly well aligned. Now there's still some motion in there, so there's still some jumping around in the different parts of the image, and we'll get to that. But now, if I take that same slice through the data cube, this is before we did the shift alignment, and this is after. So now I've lined up my data cube, and now I can see continuous structures and the granular evolution, and they change and separate as the convective flows change over time. But you see they're nice. You see the continuous features running through this XT slice, and so that tells you that now it's fairly well, at least it's rigidly aligned pretty well. There's still some jumps at times in here, but overall now we see a nice consistent pattern in these looking through time, and we're confident we have the images fairly well aligned rigidly. So that's good. So now we can, we've gotten everything well aligned, so we don't have these jumps caused by the atmosphere, AO, in there. So the last step we're going to talk about here really is this taking out those little subfield motions, the de-stretching, right? So as Jose was saying yesterday, AO is locked on a point here, the normal AO. This is without the multi-conjugate. AO is locked on some point here and keeping that fixed. But the rest of these paths through the atmosphere are slightly different in what they're seeing. And so the wavefront changes slightly, and you get different tilts of the wavefront. And that causes different parts of the field of view to have slight shifts in the over somewhat that same isoplanatic patch, that same coherent area. But it causes these little subfield shifts that we can take out if we want to get an even more stable image. And as an example here, we'll what you can get with de-stretching, just to show you. So here are these subfield shifts. And so now you see the image overall is stable, but as you look in one particular spot, you see a little bit of the image moving around over time. Play that again. And so what you get after de-stretching is this image, the sequence on the right. So that's actually the same time series, but now it's gotten much more stable, and you don't see that subfield motion anymore. So that would be nice to be able to correct for that, of course. Yep. So that's part of the trick here. Whereas, so the question was, how do you distinguish now whether that subfield motion is real or whether it's an actual motion? And this is, as I was saying, this is part of the problem of trying to separate out solar and atmospheric things, and it gets tricky sometimes. For the shifts, right, we were able to see in a time series these changes. Here, what we're going to look for is any motions on the sun should have at least some, in most cases, some coherence over time, where if they're real motions, they'll be, if I sample in time, I'll be able to see that that's something coherent on the sun over time, whereas these motions should be, for any given sample, randomly distributed and oriented, and shouldn't have any real coherence from one time step to the next. Even over 100 milliseconds, those motions will change their amplitude and direction. So my cadence, these images are this was a sample every 11 seconds. But these motions tend to be very, the time scale of their coherence is less than 100 milliseconds. So, and we're going to use that now to try, or that's what we use to try to separate those two out. So basically, sort of like AO, we divide things up into a lot of subfields. In this case, we're dividing it up in the image plane, and we're taking little boxes across the image, and we do the same cross correlation that we did on that global image. Now we just do little small cross correlations on each subfield and measure those same XY offsets on each subfield. You need to pick how big should your subfield be. That depends on what the size of the isoplanatic patch is, how big the spatial coherence of those motions are. You can't get too small or you start to run out of solar structures to track on. As you get down to too small of a box, we don't resolve any structures that will have a good signal in the cross correlation. We also sometimes use a series of nested boxes and do a sequence going from larger to smaller boxes, so we capture the large motions that are coherent over a larger area, and then once those are taken out, we can more easily find the smaller motions on the smaller boxes. But the output, the goal is to find the vector from each of these boxes showing the direction of the drift. And then once you have that, you apply that as a warping to the image. It's basically a 2D warping map that's applied to the image to remap it, sort of that rubber sheet, kind of like AO where they have the deformable mirror, but here we are able to do it, rewarp the image. It's the same way when they make the Google Earth, when they take the satellite image and they warp it to show the mountains or so on. It's applying a similar sort of distortion, a series of vector distortions across this grid and remapping the image. One thing that came up that we were discussing yesterday was whether AO at different wavelengths operates differently, whether the shifts are that the AO is seeing and that wavelength dependence. It made me wonder if the vectors of these d-stretch, right, at each point we're calculating some vector offset. And so, I just calculated the magnitude of the d-stretch vector at two different wavelengths going back onto the same reference. And the magnitude is the same in these two different wavelengths, and the direction of the vector is the same. So we can apply the d-stretch that we measure at one wavelength at the same time to another wavelength if necessary. So the question is, as I measure these vectors now, and I do this at one time step and then another time step, and I build up a whole time series of these shifts over time, and then I could apply those the same way I apply my shifts. I just apply those at each, accumulate those and apply those at each time step. And if I just do that straight directly, it starts to stabilize the image, but then things go horribly wrong. Now instead of fixing the image, it is warping things in a bad way, and that is because there are, in those d-stretch vectors, when I'm measuring the cross correlation between these subfields, there's also a steady state or a motion of the sun that's constant over some amount of time, and so it's picking that up in the d-stretch vector. It's seeing these flows that are going across the sun and trying to take those out, but when it does that, it ends up distorting the image because it's moving granules to where they were at the start of the sequence when the granule itself had physically moved on the sun to somewhere else, and so it's smearing them back. And so you see, if I take a time series and I just take the average of all those d-stretch vectors, all the random motions from the terrestrial effects will average out, and what we're left is these flow maps that have been used to measure granular flows. So you see there's sort of there's an outflow here from different areas and different supergranular cells here, and so when it's trying to make this the movie here tries to do that de-stretching. it ends up those flows end up, in these areas start just being a big problem. So what we do is you take out any cumulative motion, any gradual flow that persists over time. We fit that with a polynomial or smooth it, take that out, because we assume that's solar motion. And so if we do that and take out the flows, and these flows will also evolve in time, so that's why we can't just take out the average, we have to take out a gradual fitting to those motions, to the steady or the time averaged motions. And if we do that, now we get this, now our time series is much more stable. We see this flow. You see, because the image was moving, now our border jumps around a bit, but the central part, we can cut out the constant area here. And so that's the goal of de-stretching, is to try to take that out. We probably don't, so we don't have time to actually do this whole time series. De-stretching, it's a lot of cross correlations, and it's not well parallelizable because they're all so small, right? You have boxes are typically, defined by this kernel, so 32 by 32 pixels. So it takes too long to spin up another process to do that. It's not an efficient process, but you can measure these, do the de-stretching, and you can just try it on just a single image, or you can loop through and do it on multiple ones. That time series, the 100 images you have, is short enough that those flows, they really come in longer time series, so you don't have to worry about taking out that time average or fitting anything to take out the flows. So these are sort of the steps you can go through to try to de-stretch two images. You just pick out some image index. This is, as I said, is your kernel. So this is 32 by 32 pixels, so about 3 by 3 arc seconds in these data. You can try different sizes. You could try, taking a big box and seeing how well that does. It leaves a lot of the small scale motion. You can try going down to a 16 by 16 or smaller box, and that often has problems because some of the motions are bigger than the box or the half box size, so it can't really resolve those. They're too big. And you just run this program called REG. And that should, you'll need to compile that just because how it's done beforehand with that .run reg.pro. There's two interesting outputs. Maybe these have the node positions that it's calculating where those boxes are centered on. This gives the nominal position of the box and then where it was shifted to. So the difference of those two tells you the amplitude of that de-stretch vector. And then what you can do to see if you've actually made the data any better is you take you can take the original image. So this was your imnum, the original image you were working with, and subtract this reference image, and you should see a lot of intensity variation across that image where the gradients are because the two images are shifted. And then if you do that same thing with the output of this, the de-stretched image, you should see a lot smoother, just mostly just the noise, the photon noise and read noise in the image. And so then you'll see that'll be, that indicates that the de-stretch has properly worked and taken out those motions. And you can flicker back and forth between them and see just how much distortion there was in your image and how much is taken out. So this, you can do that on that data you aligned or the original data. They're close enough in general that both should work in this case. And then try de-stretching. The black magic of de-stretching.
I
Yes?
On which time
the solar motions. It'd be a time scale where the flows are moving your feature something comparable to your block size, right? So if you're, typically, if it's for the current resolution data past 10 minutes is probably, you need to start, you need enough samples that you can apply some smoothing through it, right? If you only have a few images to de-stretch, you don't have enough to distinguish from, there's some.
So you expect something with the resolution of the case will be much shorter?
It could be shorter, right? I mean, what's the temporal resolving element of the sound crossing time will be shorter. So here we're talking about, the granular motion across on a, some mesoscale. If we're starting to de-stretch on the edge of a granule in our box and the other edge of the granules in another box, now the amplitude and the character of those flows is somewhat different. So we'll have to figure out what the times are, but the process should be the same. I mean, it's all that the flow should have some steady behavior in time if they're solar, and the random stuff we want to get rid of. But yeah, sometimes just like you're at the, Phil was talking about working at the diffraction limit spatially you have to, there it's a signal to noise problem. Here, if you're working at the temporal resolution limit and you're trying to resolve things that are happening from one frame to the next that are, in your data, you have to be careful whether that's real or not. So, any other questions? So, yeah, this is the last exercise. So, just try de-stretching one image, see if it works, and then we'll break for coffee, I think. Yeah.
Perfect.
Then we'll stretch.
Kill the moment.
No, that's just where that's not pushing back. Yeah, from the center to the centers. 498, 499. It is, yeah, but it can possibly. But yeah, because so what I did was you take the diagonals from the center and then you work out triangular distance. So you just do Pythagoras work out what the perpendicular is away from the center. Yeah. But and then I'm just so what
I'm going to pick on mine at the end, so I'll do this again. Mine's going to pick on itself.
Nice.
It's just human list.
Yeah.
What are you trying to do?
I was thinking if I was in Boston doing the VPN, I could SSH to anyone else in the network without using the door.
At least I knew like my screen like
That's what I was testing. But I was turned off, like, why is it not responding?
That's, yeah.
it's the stars, man.
Oh yeah, I mean, finished. I got a baby grab.
See baby grab? It's a baby grab. I'll produce the same baby grab.
Yeah, I think the reason it's different from this, I'm going to actually have a look at Dean's idea. See how they do the personalization. Focus on your transfer.
Wait, are you supposed to traffic against the same image?
But,
No.
no, it's just always the one before it.
Good, that's fine. That's all I was
Tracking
doing.
it through a giant series.
Yeah, that's fine. Good. I was like, hold on.
What? The PDF should be there. And for today's, it should be.
You have to reload.
Might have to reload it.
Yeah.
Mm.
You have to get the new things, you have to reload.
Yeah, it's very latest.
Is that community?
No, that's it. It started.
I never even got asked. They're cutting the kitchen way down.
Are people seeing this when they run the reg? All the little boxes, these are where it's placed all the centers of all the subfields.
Oh, I'm sure. A lot of things. I don't like it at all. Yeah. All right. Oh yeah, it's just that one. Great.
Yeah, so that's, I just want to run. Just finish this. I'll show them
Everybody can hear the phone call. Through microphone. Oh,
It's dead now. Should be stopped.
Oh, yeah.
I would mostly put them all in little faster than them. So, you might make some
So that actually does involve.
super fast.
Okay. So we'll finish up here so we can get to the coffee break. So was anyone able to get it de-stretch 2 images? You did? So yeah, if you do the whole time series, then this is sort of what you would get out. There we are. So if you compare that, where was our? If you compare that to our original data, right? So this was the original, the starting data with the bad frames and the image motion and all the jitter. So through a few easy steps, we've gotten down to this. So it is possible to recover a lot of information about the sun, separate out those solar motions. One thing we didn't, so yeah, we'll stop there, but just I want to mention the next step in the image processing, if maybe the image reconstruction is another process that can be applied to the data. And just show you an example here. So you can have a time series of images. So these are the raw images over there, or not the raw images, but say the flat fielded instrumental corrected images taken in H-alpha. And you can apply what are called image reconstruction techniques. The two key ones we use are either speckle reconstruction, which uses information on the statistics of the atmosphere and needs a burst of images from 20 to 100 images. Or you can use something, blind deconvolution approach, or a multi-object blind deconvolution approach that again uses multiple images in order to try to, again, like the de-stretching, have different realizations of the atmosphere and assume that there's some constancy from the underlying solar image, so you can separate out what's the turbulent atmospheric effects and what is the solar image, and you get nice diffraction-limited imaging over the whole field of view. So AO may only be correcting the center, but it is possible with the image reconstruction to get a nice uniform PSF, get close to the diffraction limit over the full field of view of the image. And so that requires typically a lot more processing. Speckle has a reasonable amount. The blind deconvolution is solving a system of linear equations, and it takes significantly more computing power. So especially for the 4K images from DKIST, it will be a bigger challenge. So I think that's it. We can go get coffee now, unless anyone has any questions.